First one is the exam number 3 is 1 week from tonight. We have exam number 3 1 week from tonight, and we have one more topic to cover, which will start today. And then the final exam is 2 weeks from last night. So we've got, it's time to hit the books. It's going to be intense from here on out, because you got the exam 3, and then less than a week after that, we got the final. So there's a big chunk of your grade in those 2 exams. So we really want to start studying early. So I'm going to post a homework for the over break due next Wednesday. You need to get started on before Monday, and then also I'll post the review outline for exam 3, so you can start looking at that too. Okay, any questions before we start? Okay, we're going to go fast. It's going to be pretty, it's going to be a lot of stuff today. I'm going to kind of go fast because we need to. So keep your attention level high. Okay, so here is, in GC, if you put this equation into GC and hit graph, this is what you get. This is what you get. Why? So why, when you put this equation in, do you see this? Is that the name of this graph? Is that the name of it? That's my experience with lots of students. When they see an equation like that and a graph, there's kind of this implication that, okay, here's this graph and that equation is the name of it. Or is there more to it? Is there more to it? There's more to it. Okay? What's the connection between that equation and that graph? It goes back to what we talked about in the very first week of class. What is a graph? What is a graph? Jacob.
Set up just a bunch of points.
Okay, so the key thing here is that what you're looking at on those axes is a set of points, an infinitely number of points. So what do those points, all those points have to do with that equation? Yeah.
And the points are created from the equation.
Okay, they're created from the equation, but specifically, what do those points have to do with the equation? Yes, sir? Right, so any ordered pair, if you picked any point on this graph, say this one right here, and you took that ordered pair, you'd have an x and a y. If you substituted those x and y into this equation, it would make the equation true. But if you took a point that's not on the graph and took that x and y, and you plugged it in, the left side would not be 7, right? So any point on that graph will make the left side of that equation 7. And any point that's not on that graph, put in those x and y coordinates, you will not get 7. Okay, so the equation and the graph are mathematically the same because they're the same set of ordered pairs that make the equation true, and when plotted, give us this curve. All right? So does this set of ordered pairs represent y as a function of x? Does this set of ordered pairs represent y as a function of x? Yes or no? No, because it's easy to see, like around 3, 2.5, 3.5, all those x values give more than one corresponding y value, and that violates what we know as a function. Function means that for every x, there could only be one y. Okay? So y is not a function of x. Is it valid to talk about the rate of change of y with respect to x? Is it valid to talk about the rate of change of y with respect to x? So right here, is it valid to talk about rate of change of y with respect to x? What about here? Right there, is it valid to talk about rate of change of y with respect to x? If we look, think about at the moment, right? So in this little moment, sure. In fact, anywhere here, even though there's multiple y's for the same x, if you isolate a particular point on the curve, it's totally valid to talk about rate of change of y with respect to x. At any point, y is changing at some specific rate with respect to x. Now, except for where, right? So for a change in x, y doesn't change, so we call it a vertical tangent. There's one here and there's one here, so there the rate of change is undefined. But anywhere else, it's perfectly valid to talk about y as a change. What about a rate function? Could we have a rate function? Well, y is not a function of x, so we can't have a rate function as a function of x, right? Because you get here to x equals 3, again, what's the rate? Is it this one up here? Is it this rate here? Or the rate represented down here? But we can have a rate function if that rate, if its rate is dependent on what? A particular ordered pair on the graph. So we still can make a rate function if our independent entity is no longer just x, but a given ordered pair, x and y. Then we can talk about a rate function. So the rate function, the rate of change could be a function of the ordered pair x and y, and that makes sense. But we can't talk about rate as a function just of x, just like y is not a function of x. Okay, so then that's what we want. So we've got an equation where y is not a function of x. We want the rate equation, right? We want a rate function, and it's okay now that that rate is dependent on x and y, right? Ordered pairs. Okay, so in order to determine this rate function dy dx, we're going to suppose that y is a function of x. So it's kind of like we know it's not, but just suppose it is. Suppose it is, and then y as a function of x is implied, but it doesn't necessarily exist. All right, so we just have to kind of assume that it exists. Suppose that it exists, although we know that, like in a case like this, it doesn't. All right, and so then this is what leads us to do what's called implicit differentiation. Implicit differentiation is we're still doing the derivative, we're still finding the rate of change, but y as a function of x is only implied. It's not real. Okay, it's not actual. It's only implied. So let's do it for this example. So the whole point is we don't have y as a function of x. We have this equation, and the y's and the x's are like intertwined. They're like, and we can't be very difficult to pull these apart and get y as a function of x. Okay, so we're going to work on it like this. We're going to work on it like this. We're going to follow the same rules, but we're going to work on it in its current form. So the fact that y is an implied function of x, so we can replace y's. For this first example, we don't have to do this as we get good at this, but just so we get the point that any place there's a y, now we're saying, okay, we're supposing that that's some function of x. If we could take that equation and solve it for y, it would be this f of x, okay? If we could get that function solved for y, it would be this f of x. So then this equation becomes that. And so now we're going to follow all the same rules. We're going to take the rate of change of the whole left side and the rate of change of the whole right side. And now we're going to follow all the rules that we've learned for the mastery test, okay? It's just we're going to do it on both sides of the equation instead of only on the right side of the equation, okay? So what's the derivative of x squared? 2x. So first of all, what's the structure of this? Sum or difference, right? So we're just going to do them one thing at a time. We know that's easy, right? So the derivative of x squared is 2x. All right, so what's the derivative of f of x quantity cubed? What do we have to use to do that derivative? Power rule, but also chain rule, right? So this is the chain rule because it's not x cubed, it's some function of x cubed. Okay, so we're going to do what? Plus, do the power rule, 3 f of x, what? Squared, but then times the rate of change of the inside. Well, the rate of change of the inside is just say f prime of x. Okay? What about the next thing? Minus 2x times f of x. How are we going to take the rate of change of that? That's a product, right? Product rule. So we're going to do, this is times. So it's going to be minus rate of change of the first times the second plus the first times the rate of change of the second. Okay? And then that's going to equal the rate of change of the constant 7. 0. So did you see what I did? We just did rate of change of x squared. We did rate of change of some function of x cubed, which was chain rule. And then we did the rate of change of 2x times the function of x, which is product rule. And then the rate of change of a constant is 0. So what were we after? We're after the rate of change function. Well, we see that. This is what we want. We want this. This is the rate of change function, f prime of x. So what we're going to do is we're going to isolate all the terms that have an f prime of x in them, and we're going to get those to the left side of the equation. Any term that doesn't have an f prime of x, we're going to move it to the right side. So this is the key step. We're trying to isolate f prime of x. We want f prime of x equals something. So we get all the f prime of x terms, get them to the left. Anything that doesn't have an f prime of x, get it to the right. Okay, so it looks like there's 2 terms that don't have an f prime of x and 2 terms that do. So this is the first one. We're going to leave it on the left. So we got 3 f of x squared times f prime of x. And then this minus carries into these parentheses, right? This is minus the product rule, so minus 2x f prime of x. And then anything that doesn't have an f prime of x is going to go to the right. So we're going to subtract 2x from both sides, minus 2x. And then this is minus 2f of x on the left, so it's going to be plus 2f of x on the right. Did I do the math right? If I make a mistake, please. If I make an algebra mistake, please speak up. But I think that's right. Okay, so what now? Again, what's our goal? F prime of x equals a function of x and y. So what are we going to do? Pull it out, factor it out. So we got f prime of x times what? 3 f of x squared minus 2x equals minus 2x plus 2 f of x. So here we got it. All we have to do now is divide by this whole thing in parentheses to solve for f prime of x. So f prime of x is minus 2x plus 2 f of x all over 3 f of x squared minus 2x. Okay? But what is f of x? From the beginning, we put in f of x because this is the idea that our y, we could have solved for y and got that function of x. So that's what y is, right? So this is just y. So is this. So we get minus 2x plus 2y over 3y squared minus 2x. So what is that expression right there giving us? What does that expression right there give us? Why did we do all this pencil pushing here? What is this going to give us? Someone in the back. What was the point? Yeah. Right. So this set of points creates a graph, and we want the rate of change, right? With the rate of change. So what do we say? It's going to be a function of ordered pairs x and y, not just x. So given any point on this curve, So say 3, whatever this is, 3 and, I'll just suppose it's 0.3 or 0.2. Okay, I don't know that for sure that's right, but that's close. Okay, so there's the 0.3, 0.2. If we plugged in 3 for x and 0.2 for y, what would you predict the result would be? About what value by looking at that graph? Can you predict that rate of change right there? Positive or negative rate of change? Positive around what value? About 1, right? For a change in x, you get about the same change in y. So if you plug 3 and 0.2 into this, we would estimate, I'm just estimating that you would get about 1 for the rate of change. But if you plugged 3 and 2.1, this point up here is like 3 and 2.1, you're going to get a totally different rate of change, right? Positive or negative? Negative, really large or small? Right, like point something, like negative point something for your rate of change, negative 0.2 or negative 0.3 for the rate of change. And that's if you were to plug in 3 and like say 2.1, you would get a very small negative value, right? Okay, questions on this. It's called implicit differentiation. So now when we do examples, you can just keep it as y. You don't have to write all the f of x's. But I thought it's really important the first time so you can see that, oh, it's going to be chain rule, right? Anytime you have a y, that's like f of x, and you're going to have chain rule, and you're going to always tack on, multiply on by the chain rule this f prime, or in y prime, okay? So yeah, so you can, from here on out, we can do it with y's, but it's really, I think it's really helpful to see this first time, that whenever you're taking the derivative of f of x, you're going to have chain rule, and you're going to chain on the derivative. And then we're going to isolate those and solve for that, because that's the rate of change. Questions on this example? Okay, let's just start another example, because we've got to get on to the related rate stuff, but let's just start one more example here. Here. Okay, so here's an equation. And if we were to plot all ordered pairs x and y that make this true, that means graphing it, right? So that's pretty cool. So there's the points that lie in this curve. All these points in this curve make this true, but then there's like this isolated like ring over here. And all these points over here make it true too. Okay, so let's just get started. We're not going to do the whole example because the algebra gets a little messy, but let's just do the first step of the implicit differentiation, and then I'll let you finish it at home. Okay. So what are we going to do? We're going to leave it as it is. So we definitely trying to solve this y as a function of x would be near impossible, right? The y's and the x's are fiercely intertwined here, and so to try to get this as y equals a bunch of expression of x's would be impossible. So we're just going to take the derivative as it is. So we're going to take the derivative of both sides, and so we come to this first thing, and we want the rate of change of what? Square root, right? Rate of change of square root is what? So we think of this as to the 1/2, so we can take 4 times 1/2 to the, or of the, leave the inside as it is, to the negative 1/2, what? Now, times the rate of change of the inside with respect to x. So rate of change of x is 1. Rate of change of a function of x squared, right? So this y is, it's implied that it's a function of x. So a function of x squared, rate of change is 2y, but by chain rule, y prime. That's like before we did f of x, right? So if f of x squared, that's chain rule. So we're going to do the chain rule. Do the power rule, and then times the derivative of the interior. Okay, so we got that's the rate of change of this. Now we got minus 2y cosine x. How we do that? Product rule. Rate of change of the first. Now this is 2 times a function of x. So it'd be 2, but then by the chain rule, y prime times the second. So derivative of the first times the second plus the first times the derivative of the second, which is negative sine x. That's the left-hand side. So I did square root rule with chain rule inside of that. And then I had the product rule with chain rule. Wherever there was a y, I had chain rule. Okay? Right side. Rate of change of 3. 0 plus, what do we got? 0.1 times e to the y squared. So, rate of change of e to the something is, start with e to the something, now, times the rate of change of the interior function, which is another chain rule, right? Y squared is going to be chain rule. It's going to be times 2y, y prime. Okay, so now how many terms do we have? Terms are things that we block together and separate out by addition and subtraction. So how many terms do we get from this? 2. All this stuff multiplied by 1, all this stuff multiplied by that. So what's going to stay on the left side? So when we multiply all this times this, that will be a term that will stay on the left because it's got the y prime in it. When we multiply this by 1, that's going to move over to the right. Okay, what about here? We got 2 terms here. First one is going to stay on the right. And then, what about this term? Left or right side? To the left, it's got y prime, right? So it's going to go to the left. So everything that I underlined in red is going to go to the left side or stay on the left side. And then the remaining 2 terms here, I'll circle. So we got 1 times that. That's going to go to the right. And then this. But it'll be minus, right? Minus this, which will be plus over here on the right. So that's going to go to the right. So the blue, so we've got 2, 4. We've got 5 terms, 3 of which will have the y prime. They'll go to the left. And then the 2 blue ones will go to the right. They don't have a y prime. So and then it's just pushing the symbols around. So after you get everything organized, you factor out y prime, divide, and you've got the function. So I'll just show you the answer. You can write it down, and then you can check it later. This is what you got. Okay. Okay, so, and then I've shown here, look at negative, yeah, so let's give a second to write it down. So what, this is the rate of change function after you follow those steps that I told you. All the red ones are going to go to the left, the blue ones go to the right. Factor out y prime and divide, and you get, this is our rate function. So it's called R. Okay, but I'm not going to move it. So here I'm looking at the point negative 3, 1.8. So let's look at that point. Negative 3. Oh, it's up on the ring here. So negative 3, 1.8 is right here. High or low, positive or negative rate of change at negative 3, 1.8. High or low, positive or negative rate of change? Negative, low, negative, right? It's a shallow slope, so it's going to be a rate of change that's maybe negative a half or something like that. Negative, right? So let's see if for that other GC file that I showed you, no. Here. Look. So when you put negative 3 and 1.8 into the rate function, it's about negative a half. You see that? It will spit out about negative a half. That's showing the rate of change, giving the value of the rate of change right there at that point on the little ring. Okay, another one here. Negative 0.3 and negative 0.7. Negative 0.3 and negative 0.7 is about here. Positive or negative? Prediction for the value? About 1, maybe a little less than 1, maybe a little less than 1. 0.6. So if you put in x is negative 0.3, that point in the graph, into that, the rate function will spit out the rate of change. Meaning, what? For a small change in x, changes in y, 0.6 as much, 0.6 times as much as that change in x, right? So that the rate of change of y with respect to x still has the same meaning it always did for us. It's just coming out of a much more complicated expression, but the meaning is exactly the same. For a change in x, the change in y is 0.6 times that change in x at the moment around that point, right? Just at the moment around that point. Okay, questions on this? So you should work on your own, work through that algebra, and confirm that you get that expression right there. Make sure you can get that. Okay. So this implicit differentiation is really important for types of problems that we call related rate problems. So let's talk about that. So you've read about the you've read about this tricky monkey, right? He's tricky. He kicks that ladder out, and there's a ladder against the wall, and he kicks it, and it slides down the wall. Okay? So it's 10 foot, it's flat against the wall, and so how fast is y, the distance from the top to the floor, changing with respect to x, the distance to the wall? So you see that the problem has identified for us these quantities. They're calling y the distance at any given time, the distance from the top of the ladder to the wall, this is y. And then the distance from the top of the ladder to the floor, and then the distance from the wall to the bottom of the ladder is x. And the ladder's length is 10. So it says, how fast is the distance from the top to the floor changing with respect to x, the distance to the wall? So what are they really asking us for? Like, what would our mathematical representation of that be? How fast is the distance y changing with respect to x? What is that? This is the rate of change of y with respect to x, right? Or dy dx. Or y prime. So in order to determine y prime, what do we always have first before we can determine y prime? Yeah, we always have a function or a relationship of x and y. So we need an equation of x and y. So given this setup here, if y is the distance to the top of the ladder, x is the distance to the bottom of the ladder, and the ladder is 10, what relationship, or what is the relationship of x and y mathematically? And does that always hold? Does that always hold no matter what the position of the ladder is? All right, so pause it here. Okay, so the relationship of x and y, and does it hold no matter how the ladder, where the ladder is on its way down? Someone in the back. What's the relationship of x and y? Yes, sir? Yeah, so it's Pythagorean theorem. And will it always hold? So we got x squared plus y squared equals 10 squared. Will that hold no matter where the ladder is? Yeah, it always will hold, because that ladder is always 10 feet long, and the two sides of the perpendicular legs are always x and y. All right, so we're going to have x squared plus y squared equals 10 squared. And what do we want? dy dx. So here is our chance to practice our implicit differentiation. Okay, so this one we could solve y as a function of x, but we want to practice our implicit differentiation. So you guys do this one. So find dy dx using implicit differentiation like we just did. So this is as easy as the examples come. So can you do it? Find dy dx. Go. All right, where's Catherine Fox? Catherine, how did you start on this? Did you get started? Yeah. Yeah. Okay. So you started with derivative of x squared, which was? Okay. And then derivative of y squared was? Good. Chain rule, right? This we say we imply this is a function of x. So you have chain rule, and then what was derivative of the right side? Okay. She got it. Nailed it. So we're going to do the rate of change of both sides. It's going to be 2x plus 2y prime equals 0. And then where do we go from there? Where's Randall? Yeah. What are we going to do now? That's right. So any term that has a y prime, keep it on the left. Any term that doesn't have a y prime, get it to the right. And we end up with minus 2x over 2y, or minus x over y. Did you get that? So minus x over y. So this is what? This is giving us the rate of change of the height with respect to a change in the height of the top of the ladder with respect to a change in the distance of the bottom of the ladder from the wall. Would be minus x over y. Questions on that? Right there. Okay, so how fast is the top of the ladder falling when it's 8 feet above the ground? Well, what would 8 feet above the ground be? Value of x or y? That's the value of y. So we'd have to find the corresponding value of x for that situation. So given that y is 8, we find the corresponding x, and to get the rate of change, we then plug those two in. We plug our 8 in for y, our corresponding x in for x, and get that rate of change. Likewise for 3 feet above. Okay, but we're going to cruise on here. We're not going to spend too much time on this here. But basically, you've got corresponding values of x and y for a given position of the ladder. Plugging that into minus x over y will give the rate of change of the height with respect to the distance of the bottom of the ladder from the wall. Okay, so this expression gives the rate of change of y with respect to x, or how fast the top falls relative to the bottom moving. So that rate of change is like feet per feet, right? Feet per feet. So for a change of x in feet, we're getting the change in y and also in feet. So new question: how fast is the top of the ladder falling in feet per second? So now, what is this talking about? We're talking about speed now. Okay. So we have we're entering a new quantity here into the mix, and that's time. So before, our rate of change was the height distance with respect to the horizontal distance of the ladder. But now, if we want to know the speed in terms of the rate it's falling with respect to time, we introduce this new quantity time. Okay, so time, we need the time in seconds since the monkey kicked the ladder. Okay, and then we're going to suppose that the bottom slides out at a constant speed of v feet per second. So this is constant. So does the top fall then at a constant speed? So actually the animation showed that situation. The bottom is moving out at a constant speed. Does the top fall at a constant speed? No. And is y increasing or decreasing? Y is decreasing and it's getting faster, right? So is that rate of change increasing or decreasing? The rate of change of y with respect to time, increasing or decreasing? Decreasing. It's getting more negative, right? The rate is negative because y is decreasing, and it's clearly speeding up. So it's speeding up, but the rate of change is decreasing because it's getting more negative. So you might think, oh, the rate is increasing because it's speeding up. It's a really common way to think of it. But because it's a negative rate of change, because y is decreasing and getting more negative, that rate is actually decreasing. That's a decreasing rate. Okay. Okay, so our dx dt then, so our rate of change of the bottom with respect to time is constant. That's what we're saying. It's a constant. So we're going to start with that same equation again now, but we're not doing our derivative with respect to y anymore. We're doing our derivative with respect to t. So now x is a function of t, and y is a function of t. So everything is chain rule, even when the x's, because you're doing it with respect to t. So everything is chain rule. So we're going to have 2x. How we take the derivative of this with respect to t, it would be x squared would be 2x times x prime, or times dx dt, and 2y times y prime, or dy dt. So now everything is chain ruled because of this new variable time, which both x and y are a function of. Does it make sense? Okay, and so now what do we have? We've got an equation. So if I solve that, again, if I solve for dy dt, because we're interested in how fast the top of the ladder is moving, I'm going to isolate dy dt on the left. Now we have something we've never seen before. We have an equation that has what? More than one different rate of change in it. So this equation brings together the rate of change of y with respect to t and x with respect to t in the same equation. Two different rates. Okay? So this is why we call it a related rates equation. It's an equation that relates more than one rate of change. So dy dt, how fast the top of the ladder is falling down. Dx dt, how fast the bottom of the ladder is pushing out. Two different rates, okay? And as that thing falls, this equation will always hold true for any orientation of the ladder. Okay, and so what's the source? Where did the related rates equation initially come from? This is going to be key in solving these problems. Where did we get it? From what? What was the source of the related rates equation? You should be looking at this right here. The equation that related the associated quantities x and y. So if we want to relate dy dt and dx dt, we first need an equation that relates x and y. And that was our x squared plus y squared equals 100. So this is always going to be true in these related rates equations. Figure out what rates you need to relate, and then you're going to start by getting an equation that relates those associated quantities. Does that make sense? Okay? So to reiterate, to get the related rates equation, you first must have the equation that relates the quantities associated with those rates. Okay. Questions on that? All right, so let's try an example. The edges of a cube increase at a rate of 2 centimeters per second. How fast is the volume changing when the length of each edge is 50 centimeters? Okay, the edges of a cube increase at a rate of 2 centimeters per second. How fast is the volume changing when the length of each edge is 50 centimeters? So is this a related rates scenario? Because it's relating what rates? So what rates are implied or mentioned in this situation? Yeah? Okay, so we have the rate of change of how the cube length are increasing. So 2 centimeters per second, that's a rate. That's the rate of change of the edge length to time. What is there another rate involved here? What's the other rate involved? Where's Noah? Is Noah here? Can you see another rate involved here besides the rate of change of the edge length? It doesn't have to be given, it just has to be mentioned, right? So we're yeah, how fast the volume changes, right? So we need an equation that's going to relate how fast the edge length is changing and how fast the volume is changing, right? So therefore, what are we going to need? If we need a related rates equation for the rate of change of the edge length with respect to rate of change of or associated with the rate of change of the volume, then where's that going to come from? What are we going to need? The big point of the last slide. Yeah, Aiden. What are the two quantities? Yeah. Not the rate. That's what we want. We want an equation that relates the rates. Where's that going to come from? Yeah, an equation that relates just edge length and volume. Right, exactly. Okay, so we're going to start with a quantities equation, and then from that we get the related rates equation. Okay, so we identified the rates. We did that. The rate of change of the edge length, rate of change of the volume. How fast edge length is changing, how fast volume is changing. So what quantities are associated with those rates? What quantity is associated with how fast the edge length is changing? No, that is the rate. What's the quantity associated with that rate of change? No, not time. Yeah. Well, that's the units. It's so easy, it's hard, right? What's the quantity associated with rate of change of edge length? No, that's a number. What's that? Edge length. Okay? And what's the quantity associated with how fast the volume is changing? Volume. Okay, so I was going to say obvious, but I guess it wasn't so obvious. But like, I guess easy or something like this, or just, yeah, obvious in a way, but super important because that's how we're going to get started. Okay, so we want to write an equation that relates those quantities. This is our quantities equation. What equation or relationship relates edge length of a cube to volume? Side cubed, right? Volume equals side cubed. I gotta change the slide. This is poor notation, but we'll just go with it. Okay. All right. So volume equals side cubed. I'll try to fix it on the fly. See how it goes. Volume equals side cubed. Volume equals side cubed. All right. And now we're gonna derive the related rates equation. Meaning, what? We're gonna take everything, the rate of change of everything with respect to time. So left side. What will be the rate of change of V with respect to time? Yeah, it's just dv dt. Or you could think it as the rate of change of V is 1, and then by the chain rule, the derivative of that. Or you could just say the derivative of V is dv dt. Okay? Right-hand side, with respect to time now. So he's got chain rule because side length is a function of time. And we've got s cubed. So rate of change is 3s squared ds dt by the chain rule. So this is our key to figuring out how fast the volume is changing, because it's our equation that relates how fast the volume is changing with how fast the side length is changing. Okay, so this is our unknown. So if this is our unknown, then we have to somehow be able to find out everything else. Do we know what S is at the moment in question? It says 50, right? Do we know how fast the side length is changing? 2 centimeters per second. Therefore, we've got dv dt. 6 times 2,500, or is that 15,000? What's the units on that? So the units is going to match up with our notation here. Centimeter cubed per second. Meaning, for any change in time, what? For any change in time, the volume will change 15,000 times as much as that little change in time. At this moment in question, right? At this moment in question, when the side length is 50 centimeters. Okay, so like I said, we're gonna get going on the homework for next Wednesday, and I'll post the review outline to get students start studying for the exam next Wednesday.